Quantum physics is strange. It challenges our everyday understanding of how the world works. But what if light itself could break the rules of time? Sounds like science fiction, right? Well, scientists have just discovered something astonishing. Photons, the particles of light, can appear to move through a material and leave before they even enter it. And this isn't a simple illusion. It's a real quantum effect called negative time. Let's break it down. To understand this new discovery, let's start with some basics. Photons are the particles that carry light. They're not like the little balls we might think of with regular particles. Photons are wave particles, meaning they can act like waves sometimes and like particles at other times. They travel through space, carrying energy. And when they encounter atoms, they can interact with them in interesting ways. Normally, when a photon enters a material, it can be absorbed by an atom, causing the atom's electrons to jump to a higher energy level. This is called atomic excitation. After some time, the electron falls back to its original state, releasing that energy as a re-emitted photon. So, the photon goes through a delay, and we observe that delay in its travel time through the material. Now, here's where things get interesting. There's a concept called group delay. This is the delay that light experiences when it passes through a material and interacts with atoms. Scientists wanted to measure this delay and understand exactly how much time light spends interacting with atoms. But there was a problem. Nobody knew for sure how to measure it accurately, especially when photons didn't seem to interact with atoms the way we expected. So, a team led by Daniela Angulo at the University of Toronto set out to test how light behaves in this situation. They shot photons through a cloud of ultra-cold rubidium atoms and measured how long it took for the atoms to get excited by the photons. But when they looked at the data, they saw something weird. Sometimes, the photons passed through the cloud of atoms without being absorbed, but the atoms still became excited. The atoms were reacting to the photons, even though those photons didn't seem to be interacting directly with them. And here's the real kicker. When photons were absorbed by the atoms, they seemed to be re-emitted almost instantaneously, before the atom had even finished its reaction. It was like the photon left before it had fully entered the material. Now, the most mind-boggling part, negative time. Scientists had never observed something like this before. Negative time means that the light's interaction with the atoms was occurring faster than expected, to the point where it looked like the photon was leaving the atoms before it had even finished interacting with them. Imagine looking at a clock and seeing the hands move backward. It was a direct challenge to how we think time should work. So, how can this happen? The answer lies in the quantum nature of light and atoms. In the quantum world, particles like photons don't have fixed, predictable behaviors. Instead, they exist in a superposition of possibilities. This means that a photon can both pass through without interacting with the atom and also interact with the atom at the same time until we observe it. This superposition of behaviors creates a situation where the photon's interaction with the atom can seem to happen faster than expected, leading to this negative time effect. It's not that time is actually moving backward. It's just that the measurement process is revealing this strange quantum phenomenon. To make sense of this, the researchers worked with theoretical physicist Howard Weissman from Griffith University. Together, they developed a framework to explain how and why this negative time appears. The theory predicted that the amount of time the photon spends in the atomic excited state, what we call the group delay, could match perfectly with the strange timing observed in their experiments. Even when it looked like the photon was being re-emitted too quickly, the theory showed that the overall delay could still make sense when considering the probabilistic nature of quantum events. The quantum world doesn't follow fixed rules like our everyday experiences. It's all about probabilities and possibilities. Now, you might be thinking, so what? What does this mean for us? The discovery doesn't change our basic understanding of time or relativity. No, it doesn't violate Einstein's rule that nothing can travel faster than light. But it does show just how strange and unpredictable the quantum world can be. This finding helps physicists understand how light and matter interact in even more detail, which could have future applications in quantum technologies like quantum computing and communication. This discovery also raises questions about the nature of time and measurement itself. How do we measure time in the quantum realm where things don't behave the way we expect? The study could lead to new ways of thinking about light, time, and atomic interactions. While this negative time doesn't break any physical laws, it certainly opens up new doors to understanding the quantum universe, and there's still a lot more to explore. In the end, this experiment is a beautiful reminder that the quantum world is full of mysteries waiting to be uncovered. Time, light, and reality itself are much stranger than we ever imagined. So, who knows what other surprises the quantum universe has in store for us? Thanks for watching and stay curious.